Far beyond the familiar constellations of the night sky, in a quiet region of Leo, a faint distortion in infrared light finally reached Earth after traveling for more than a century across interstellar darkness. At first, it looked routine, just another dataset among trillions collected by humanity's most advanced observatory. But buried inside that signal was something that changed everything. A chemical fingerprint that should not exist on its own. The James Webb Space Telescope had detected an atmosphere that does not merely suggest life, it strongly implies it. Not as a possibility, not as speculation, but as a statistical reality emerging from the data itself. A distant world, 120 light-years away, is showing signs of chemistry that on Earth only life can maintain. And the implications are staggering. Because if the interpretation holds, we are not looking at a planet where life might emerge one day. We are looking at a planet where life is already active, shaping its atmosphere in real time, on a planetary scale. The discovery came quietly, hidden within the spectral analysis of starlight passing through an exoplanet's atmosphere. As the planet crossed in front of its red dwarf star, Webb broke the light into its component wavelengths, revealing the molecular structure of the gases surrounding it. At first, everything seemed familiar: water vapor, carbon dioxide, methane. The usual suspects. Molecules often associated with habitability. But then came something unexpected. A compound known as dimethyl sulfide. On Earth, this molecule is not produced by geology, volcanism, or atmospheric chemistry. It is produced by living organisms, primarily marine ecosystems. Phytoplankton. Microbial life. Biology itself. And the signal was not faint. It was strong, persistent, and statistically significant enough that random chance dropped below 1 in 1,000. In astronomy, where uncertainty is standard, this is not just unusual, it is extraordinary. The planet, designated K218b, orbits within the habitable zone of a red dwarf star. But it is not an Earth clone. It belongs to a category known as a super-Earth, larger, heavier, and wrapped in a dense hydrogen-rich atmosphere. For decades, scientists assumed such worlds would be hostile. Too thick, too pressurized, too alien. But K218b is revealing a different story. Its atmosphere acts like a thermal regulator, trapping heat efficiently and distributing it across the planet. The result is an unusually stable climate. Temperatures remain consistent enough to allow liquid water to exist across large regions. There are no extreme seasonal swings, no violent atmospheric collapse, no runaway freezing or boiling cycles. Even its tidal locking, one side permanently facing its star, does not create a dead frozen hemisphere. Instead, atmospheric circulation appears to redistribute heat, keeping the entire planet within a survivable temperature range. Gravity plays its part as well. Nearly 3 times stronger than Earth's, it prevents atmospheric loss. What Mars lost over billions of years, this planet retains effortlessly. Everything about it, once considered extreme, now appears strangely optimized. The star it orbits is a red dwarf, small, cool, but astonishingly long-lived. While stars like our Sun will burn out in billions of years, red dwarfs can remain stable for trillions. That means any biological system that takes root there has an almost incomprehensible amount of time to evolve. Time is not a resource this planet lacks. It has it in abundance. And that may be the most important ingredient of all. As more data arrived, a deeper pattern emerged, not just chemistry, but imbalance. The atmosphere is not in equilibrium. Methane and carbon dioxide should react and stabilize over time. Dimethyl sulfide should break down under stellar radiation. Ammonia should be present in hydrogen-rich environments. Yet none of these systems behave as expected. Instead, the atmosphere is actively maintained in a state of disequilibrium. On Earth, this condition is a signature of life. Life constantly injects gases into the atmosphere, preventing it from settling into chemical stillness. Forests, oceans, microbes, all participating in a planetary scale cycle of renewal. K218b shows the same structure, but on a vastly larger scale. This is not a trace of life. It is evidence of a system sustained by life. A living atmosphere. A breathing planet. A biosphere so large it reshapes the chemistry of an entire world. The most unsettling implication is not just that life may exist there, but that it may dominate the planet. Not scattered microbes in isolated pockets, but a continuous, planet-wide biological system. A world where biology is not an exception. It is infrastructure. For decades, the search for extraterrestrial life focused on Earth-like conditions: rocky surfaces, oxygen atmospheres, moderate temperatures, sun-like stars. That model is now collapsing. K218b does not fit that template. It exceeds it. It suggests that habitability may not depend on similarity to Earth at all, but on stability, chemistry, and time. In fact, Earth may not be the standard. It may be the exception. One of the most compelling aspects of the data lies beneath the surface assumptions. Hydrogen-rich atmospheres were once considered incompatible with complex life. Too reactive, too unstable, too chemically chaotic. But on this world, hydrogen does something different. It stabilizes. It thickens the atmosphere, creating a massive insulating layer that smooths temperature differences, shields radiation, and supports long-term climate consistency. Far from being hostile, it becomes protective. A planetary blanket that allows chemistry to persist long enough for complexity to emerge. Beneath this atmosphere likely lies something even more extraordinary: vast global oceans. Not shallow basins like Earth's, but deep, continuous water layers potentially extending hundreds of kilometers downward. Under immense pressure, mixed with dissolved hydrogen, water behaves differently. It remains liquid under conditions that would crush or freeze Earth-based systems. This creates an entirely new kind of environment. A planetary ocean without continents. A continuous liquid world. And within it, energy gradients may drive biological processes independent of sunlight. Life here would not depend solely on stars. It could draw energy from chemistry itself, from deep ocean interactions, from atmospheric exchange. Entire ecosystems could exist layered through depth. Surface organisms interacting with the atmosphere above, deep organisms thriving in high-pressure chemical zones below. A biosphere not spread across a surface, but built through volume. Three-dimensional life on a planetary scale. The dimethyl sulfide signature detected by Webb becomes even more significant in this context. It is not a stable molecule in space. It breaks down quickly under radiation. To maintain detectable levels across interstellar distances requires constant replenishment. On Earth, that replenishment is biological. On K218b, if the same mechanism applies, the scale of production must be enormous. This is not a planet with isolated ecosystems. It is a planet where biological activity defines atmospheric composition. The atmosphere itself becomes a metabolic system. A planetary organism in function, if not in form. Perhaps the most profound shift this discovery forces is temporal. Earth's biosphere is young in cosmic terms. Complex life emerged late and remains fragile. But red dwarf systems change that equation entirely. These stars can remain stable for trillions of years. If life begins early on such worlds, it is not constrained by the narrow window that defines Earth's biological history. It has time. Immense time. Time to evolve complexity, stability, and scale far beyond what we know. K218b may not represent early-stage life. It may represent maturity. A biosphere that has already passed through billions of years of evolution. Not primitive. Not emerging. But established. Stable. Integrated into its planet so deeply that atmosphere, ocean, and biology are indistinguishable. This reframes everything. We are not witnessing the beginning of life elsewhere. We may be witnessing its standard form. A universe where life does not struggle to exist, but persists wherever conditions allow it to stabilize. The emotional impact of this realization is difficult to overstate. For centuries, humanity assumed the cosmos was silent and empty, with Earth as a rare exception. But K218b suggests the opposite may be true. Space is not empty. It is structured. Populated not necessarily by intelligence, but by biology on scales we are only beginning to understand. And if one such world can be detected so clearly, others are almost certainly waiting to be found. This is not just a discovery. It is a threshold. A transition from speculation to observation. From probability to evidence. From possibility to pattern. The universe is no longer something we imagine life within. It is something we are beginning to observe life across. And perhaps the most unsettling conclusion is this: we were not looking into a silent universe. We were simply not yet able to hear it.